So I actually told a friend that I began this class by asking you an irrelevant question, and I failed to do so, thanks to Stefan, by my own fault. So the irrelevant question was, how many of you have heard of a Frito pie? Frito pie? Frito's pie? Frito pie?
Yeah, actually.
Yeah.
Okay, I'm just curious. How many? Just raise your hand. Okay, thank you. Okay, because yeah, the implication was that I wasn't American because I hadn't heard of Frito pie. But okay. Yeah. Okay. So what?
I'm just curious now, like, what that looks like.
What a Frito pie looks like? She showed me a picture right there. You know, I said, "You've got to be kidding!" What?
Yeah, the most disgusting thing.
Okay. Well, I'm not gonna. I told her I'd show her this part of the video. So reactions to that question. Okay. Okay. So let me start off with something. So a little bit of a digression. If we have some number 0.9, 0.99, 0.999, 0.9999, right? And we look at this thing, this sequence here. Right? You have this number 0.9999999. What is that number? What is that number? Or like, what does that number equal? Sorry?
Sorry, 1.
1? Yeah, 1, right? Is that, have you heard this before, that 1 is the same thing as 0.9999? No? Oh, okay. There are a couple ways to see it. Well, okay, so, what's 0.333333333? A third. Okay, so 0.33333 is 1/3. So you could just multiply both sides by 3. Right, and you get 1 is equal to 0.9999999. That's one way to see it. Right. There's another way we'll see shortly. But that's interesting that you've never seen this sort of thing. But basically, what this illustrates is that so let me ask this. What's the difference between these two numbers, 1 and point? Suppose somebody gives you these two things and says, are these the same thing? Are these the same thing? Well, one way you could think about it is to say, what's the difference between them? Or how big is the difference between them? How big is the difference between them? Well, right, so it's smaller, is it smaller than 0.1? Right, is it smaller than 0.01? Yeah, because the difference between these two is 0.01, and it's smaller. The difference is smaller than that. Is it smaller than 0.001? Yeah. Right. In fact, it's the difference between them. Right. You have two numbers. Here, you have two numbers, and the difference between them is smaller than epsilon for any epsilon you choose. Right. So for any number you choose, the difference between these two numbers is smaller than that, right? And we basically take that to say that they must be the same number. Okay, so we consider 1 and 0.99999 to be the same number in our real number system. So in R, so if you have two numbers, if A and B are real numbers, and the difference between them is smaller than any number you can think of, right? Any smaller than the tiniest number you think of. Well, no matter what tiny number you choose, the difference is smaller than that, and we think of those numbers as the same thing. Okay, for example, these two, 1 and 0.99 are the same thing. Okay, I should say that there are number systems where one actually distinguishes between things that have like infinitesimally small differences, but we're not going to deal with that. Okay. So there are, if people are interested in that sort of thing, you can create number systems where things, you can talk about infinitesimals. Okay. But we're not going to. We don't. Okay. Okay, so that's one thing I want to start off with. And another thing, okay, so just for fun, this is just for fun, and to illustrate that limits are, again, something a little bit tricky. Suppose I have a number like this: 1 minus a half plus a third minus a fourth plus a fifth minus a sixth plus a seventh minus an eighth plus a ninth minus 10 plus 11 plus 12, etc., etc., etc. Okay. There's some number that you get from doing this. Okay. And so, like graphically, I start off with 1, and I drop down a half. Like here's 1, and I drop down a half, right? And then I add on back a third, so I don't go back all the way up. And then I drop down a fourth. I don't go all the way down again. Right? So each time I'm reducing the change. Right? Each time I'm reducing the change. And I go up a fifth minus a sixth, etc., etc. And I end up with some number. Okay. I end up with some number. It's not 0. You know, it's bigger than a half. You know, it's smaller than a half plus a third, etc., etc. I call that number gamma. Okay. Just for fun. Okay. Suppose we make this number gamma, and the second thing we do is we look at a half gamma. We look at a half gamma. Okay, so half gamma, 1 half minus a fourth, plus a sixth, minus an eighth, plus a 10th, plus a 12th, plus a 14th, plus a 16th, plus an 18th, minus plus, etc., etc. Okay. Okay. So suppose I add these two things together. I'm going to get 3 halves gamma on the left, right? And what do I get on the right-hand side? Well, some cancellation occurs, right? So I have 1, the halves cancel off, right? So I get, that's nothing. I have these 2 minus a fourths, right? And these 2 minus a fourths, that's a minus a half, right? So I've got those guys. I've got this third here. I'm going to take the third, right? And then I've got minus an eighth and minus an eighth. I'm going to use those things to make minus a fourth. Okay. You don't have to copy this down. This is just entertainment. Okay. And then I get a fifth, right? Blah, blah, blah. The sixths cancel off. Right? I've got a minus a 12 and then minus a 12. I use those to make a minus a 6. Got plus a 7, plus a 7, etc., etc., right? And so what do I end up with on the right-hand side?
The exact same thing.
The exact same thing. Okay, so I got gamma, right? So I have this number. I have this number that's not 0, and 3 halves gamma equals gamma, right? So I'm going to divide by gamma on both sides. I can do it. It's not 0, right? And so I get 3 halves is equal to 1, and so I multiply by 2, and I get 3 is equal to 2. Okay?
Wait, could you do the last step again?
Sure. I had this 3 halves gamma. I added these two things together. I got 3 halves gamma equals gamma. Gamma is non-zero. I can divide by any non-zero number, right? 1 over gamma. It's not 0. I multiply both sides by 1 over gamma. I get 3 halves equals 1. Right? If you want to stop there, but if you just to make it even more appalling, you can multiply by both sides by 2. Right? We can stop there. 3 halves equals 1. Okay, that's the end. So what? No, I should ask. I should ask. What went wrong? Did we do anything wrong? Did we do anything wrong? So this is just to illustrate that when you're dealing, again, when you're dealing with infinity, you have to be a little careful. And this is actually something called an infinite series. It's one sort of a limit. This is one sort of a limit, right? You let the numbers, you have an infinite number of numbers that you're adding together. Okay, this is called an infinite series. We'll deal with them later. One has to be careful with dealing with limits. And really, what goes wrong here is basically that we're thinking of infinite arithmetic as the same thing as finite arithmetic, right? That I can just cancel things off as I feel like, but in fact that doesn't work. That if you are so reckless with it, then you end up with false statements. Interestingly enough, so this is why people really needed to talk about make the notion of limit precise. Okay, so now let's get back to the limit. Okay, so recall that if the limit of f of x was L as x approaches c, what this meant for us was that then given, so here's the picture, here's C, here is L, okay. What this meant, and let's draw a picture, say, like this. What this meant was that if somebody gave you an epsilon and said, I'd like you to stay within these, I'd like your outputs to stay within epsilon of L, then you could find a delta so that all the points between C minus delta and C plus delta satisfied that tolerance, right? That was the moral of the end of last class, right? I think we had something like this, right? We had something like this and said, how close do we have to be to 0, right? The slope, it was something like f of x equals 2x, and if somebody said, right, I think this is what we did last time. If somebody said, I'd like you to stay within 1 of 0, right? Well, how close must the inputs be to 0 to ensure that the outputs stay within 1 of 0? Stefano? 0.5. Like 0.5, right? As long as the inputs stay within 0.5 of 0, the outputs stay within 1 of 0, right? As long as the inputs stay within 0.5 of 0, right? As long as the inputs stay within minus a half and plus a half, well, then the outputs are going to stay within 1 of 0, right? And, yeah?
Is the reasoning correct if I say, like, I do the opposite of what's being done to x to get that value?
I don't want to. Let me not get into that right now. We'll get into more detail in a second.
How would I get to that other one?
Let me get to it in a second.
Oh, okay.
Let me get to it. We'll get to it in just a second.
Okay.
Sorry. If somebody wanted us to stay within 2 of 0, right? Suppose somebody says, I'd like you to stay within 2 of 0. How close do the inputs have to be? If you want the outputs to stay within 2 of 0, the inputs have to stay within 1 of 0, right? And so what you see is that no matter what constraint is put on you, you can find a place where that constraint is satisfied, right? If somebody says, I want you to stay within, 0.1 of 0, I want you to stay within 0.1 of 0, how close must the inputs be to 0? To make 0.1. 0.05, right? It'll be half of that, right? Okay. Is everyone following? So the point is that if the limit really is 0, then given any number epsilon, any tolerance epsilon, one can find a delta so that f of x minus L is less than epsilon whenever x minus c is less than delta. So let me try and say it again. Okay, let me try and say it again. Here's the picture, right? Suppose this thing has slope 2. Suppose this thing has slope 2. Somebody says, I'd like you to stay within, if somebody says, I'd like you to stay within 2 of 0, right? I'd like you to stay within 2 of 0. Well, you can find a place where that happens, right? That will be this point plus 1, this point minus 1. Right? As long as you stay within 1 of this point, the outputs will stay within 2 of 0. Everyone following that? Please stop me if you don't. Everyone all right? I'll show you, okay? Okay, good. Again, don't, I can't read facial expressions at all. So.
Wait, so is that true in every, sorry, is it true in every case or just this specific line? Like that it's within 2?
Just this point here. Just this
Okay.
point here. I mean, it's. Let's just think about this point here for right now.
Okay.
I mean, certainly it's true for every point on a line. On a line, it will be true for every point. But let's just ignore that right now and just think about this point right here. Okay. And if somebody said, I'd like you to stay within 1 of this point, well, how close? Can you find a region around here? How close must you be to this point to ensure that the outputs stay within 1 of 0? The slope is 2, so you can, at most you can move 0.5 away, right? You move 0.5 away in either direction, then as long as you move less than 0.5 away in either direction, then your outputs are going to stay within 1 of 0. Right? That's basically what the slope means, right? If we move 0.5 here, the output is going to move 1 away. So if we move less than 0.5, then the output is going to move less than 1 away. Okay. Now suppose somebody said epsilon. I'd like you to stay epsilon away. At most, I want your outputs to stay within epsilon of 0. Well, what's the answer? Half of epsilon, right? Half of epsilon. You can take your delta to be half of epsilon, right? And as long as you stay within half an epsilon of here, then your output will stay within epsilon of here. Okay. Everyone following this? This is the key. This is the key. Okay. Anyone at all confused? Don't be embarrassed if you are.
Wait,
Yeah, Mariah, go ahead.
I think I understand, but
Yeah.
if you have a line with like a not constant slope, does this still work?
A line with a not constant slope.
Yeah,
I mean, a
like-
function with a not constant.
Yeah, I'm sorry, a
Yeah,
function.
Yeah.
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 Does this rule still work?
So, if the limit is actually L,
Mhm.
then you'll be able to find a delta. So suppose we have something like this. Okay, here we are, right? And somebody says, I'd like your outputs to stay within one of L. L plus 1, L minus 1. Can you find a delta that works? Well, I'd say you just sort of eyeball it, and you'd say, oh, look, as long as I stay between here and here, my outputs do satisfy you, right? And the person would say, well, what about like this? L plus this little thing and L minus this little thing. You'd say, well, I think I can still do it. I can find a delta that works. Okay. And so the thing is that if you can do this for every tiny distance, that's what we're going to use as the definition of limit. That's what we're going to use as the definition of limit. So we'll say, so if, let me say it this way, if given any epsilon, this is the definition. This is how we will define the limit. If given any epsilon greater than 0, there is a delta greater than 0, so that whenever x minus c is less than delta and greater than 0, one has the distance from f of x to L less than epsilon, then we say the limit of f of x is L, as x equals c. So this turns out to be how we define the limit. This is the definition of limit. Let me just add in one small thing here. We can rewrite this as the distance of x to c is less than delta and greater than 0. Here we're saying the distance of f of x to L is less than epsilon. Just to write this out in English. Write this thing out and this thing out in English. Okay. Claire, you had a question first.
Oh, I was just wondering, so when you were doing this, you had the L plus 1 or something and
Mhm.
L minus 1.
Mhm.
Wouldn't the point on the x-axis be like farther out because it doesn't even reach 1 until like farther?
Oh, you're saying couldn't we use a bigger delta?
No, I'm saying like, so to find out where like the x values where that is still within it,
Mhm.
don't you just like trace the function until it gets up to that point and then drop down to see the x?
Yeah, you could, but the trouble is that you want it to be a balanced. You want it to be symmetric on both sides.
Oh, okay.
Okay, so I actually don't want to go too far. If I choose a huge
Because like there's still, the function is still below.
Sure. So it works over here.
Yeah,
But-
but it doesn't work over there.
Right. It doesn't work over there, and all that matters is that you find some place where that tolerance is satisfied.
Okay.
Okay. So, you don't have to find the best place, just
Okay.
some place where it's
Okay.
satisfied. Somebody had a question over here. Yeah.
Will delta always be epsilon over the slope?
Will delta always be epsilon over the slope? If it's a line, yes. If it's a line, that's always going to be the case. Yeah. Mariah, what was your question?
So you use this to prove that a limit exists.
Yeah, you use this to prove that a limit exists.
So what would it look like if the limit didn't exist? Like what would you get?
It would be impossible to find a delta that works.
Okay.
Okay, so
What would that look like?
so let me.
I thought you could always find a delta.
No. So suppose you have some function like this. Suppose you have some function like this. Here, our intuition is limit doesn't exist. Limit doesn't exist. Right. And let's see how this thing fails the definition. Okay? Right. This thing had better fail the definition if this is a good definition. Okay. So here is C, and what are you going to take as your L? Is this going to be your L, or is this going to be your L? Doesn't matter. Let's take this one to be your L. Okay. Let's say that we're thinking that this is going to be the limit. Okay. Is the limit L? Well, if the limit is L, we can find then given any epsilon, we can find a place where all the outputs are within epsilon of L. Given any epsilon, we can find a place where all the outputs are within those bounds. Okay. So if I say, let's take this epsilon. Can you find the delta where all the outputs within delta of C satisfy the epsilon constraint? No, it's impossible. right? You see, it doesn't work. No matter how tiny a delta I choose, I fail on the right side, right? I can't find a neighborhood where I satisfy your constraint. And so the limit isn't this L. And you could do the same thing for this upper one, right? The limit's not this L either. Right? And so that would show that the limit, well, at least it shows that the limit's not neither of these possibilities, which seem to be the only possibilities. Do you see? Does anyone see that one? How the limit catches that this is the definition catches that this really isn't a limit. This really has this L isn't a limit. Okay. Yeah, Sarah.
So I kind of thought that a limit was like undefined point, right? So like your limit is like where you don't have like the answer, you know?
Say one more time.
Like so like it's when there's like an undefined point, I figure in the function. But like I don't know.
Say the whole sentence one more time. Maybe not.
Well, so like my definition, I was like kind of understanding
Yes.
was that like the limit is where like the function is undefined.
The limit is where the function is undefined. No, so the limit is
Yeah. So like.
so the limit as x approaches c of this function is the value, so the rough definition is the value that you get, right, the y value that you get as the inputs approach c. Okay, so as the inputs approach c, the y values get closer and closer to some value. That's the limit. Okay, it could be defined there, it could be undefined there.
Okay.
Okay, so that's what we mean as the limit.
Okay.
Okay, so that's the.
So it's just more general. So like,
This thing is more general.
yeah. That well then like just like having like any one specific point be on a function.
I'm not following again.
Never mind. It's okay.
Okay, let's talk after. Let's talk
Okay.
after. I'm clearly I'm misunderstanding something. Okay. So this is the definition of limit. Okay, this is the definition of limit. Right. What does it mean to say that the limit of f of x is L? What does it mean to say that the limit of f of x is L? It means that given any tolerance around L, you can find a place where that tolerance is satisfied. Given any constraint on how close your outputs have to be to L, you can find a neighborhood of C where that constraint is satisfied. Okay. So let me show you an example, and you've sort of seen this already, of how one uses this using the definition to show a limit is true. So here's the example. Show that the limit of 3x plus 2 is 14 as x approaches 4. Okay. So what do we need to do? We need to show this is true. We need to show that given any epsilon greater than 0, one can find a delta greater than 0, so that if minus 4 is less than delta, then f of x minus L is less than epsilon. Okay. Just following the definition. This is what we need to do. Stefan?
Epsilon always a symbol that's going to represent tolerance.
Yes, yes, that's right. And delta is always going to represent the radius of the neighborhood of the interval. Yeah, that's pretty standard. So epsilon is the enemy. Delta is your creation to defeat the enemy. So epsilon is some sort of negative, has some negative connotation to it. Some sort of small enemy. Yeah, in general, epsilon just means some sort of small number. Okay, so what's going to be the delta? Can anyone tell me what the delta is going to be? If I say I'd like you to stay with an epsilon of 14, how close do we have to be to 4 to ensure that? If I say I'd like you to stay within 3 of 14, how close do you have to be to 4 to do that? Who can anyone tell me offhand? This is yeah, Megan.
Would it be epsilon over 3?
Epsilon over 3, that's right, because this is a line, right? It's a line of slope 3. So ultimately, in your head, you actually know the answer to this, right? How close do I have to be to make my thing vary by less than 3? Well, it have to be, you have to move only one distance away, right? If I ask you to stay with an epsilon, as long as you move less than epsilon over 3, it's going to work, right? Because the line has slipped 3. Right, so to ensure that it move less than epsilon, as long as you stay within epsilon over 3 down here, the thing is going to move less than epsilon up there.
Can you explain that? Writing the whole how you get from one to the other.
Yeah. So that's just the intuition, and right now we'll do it if we have no geometric sense at all. Okay. So one has to be able to do math even if you're completely blind. So in fact, I know at least one blind mathematician, and there's been some famous ones. Okay. Okay. So we want delta so that if this, I'm just rewriting this, then this. So here's how you do it in your head if you were blind, say. If you couldn't see what's going on. If you couldn't see what's going on, such thing. Okay. You'd say, well, look, let's look at this thing. 3x plus 2 minus 14 is less than epsilon. Okay. I'm just gonna play around with that a little bit, right? That's 3x minus 12 is less than epsilon. Right? Okay. That's the same thing as 3x minus 4 is less than epsilon.
You take the 3 out of the absolute value. How can you take the 3 out of the absolute value?
Oh, the absolute value of the product is the product of the absolute values for any numbers. So
And the absolute value of 3 is just 3.
absolute value of 3 is just 3.
Okay.
So you can do that. Okay. Everyone all right? Right. This is the same thing as that, right? And that's the same thing as saying that x minus 4 is less than epsilon over 3.
Could you say?
So let's look at this thing up here, right? 3x plus 2 minus 14 is less than epsilon, right? That's the same thing as 3x minus 12 is less than epsilon, absolute value. I pull the 3 out. 3 times x minus 4 is less than epsilon. Okay. So what should my delta be to ensure that if this is less than delta, then this is less than epsilon? What should right? If x minus 4 is less than epsilon over 3, then this thing will be less than, then 3x minus 4 will be less than epsilon.
Say that again.
Right? So if, so we know this, so we observe if x minus 4 is less than epsilon over 3, then 3x minus 4 is less than epsilon.
Okay.
Right? If epsilon minus 4, absolute value is less than epsilon over 3, then this is less than epsilon. So what delta do we choose? We'll choose delta to be epsilon over 3. Right? So choose delta to be epsilon over 3.
So then, do you say it like because it's possible to find that and the limit does exist?
Exactly. So, so after you do the scratch, does everyone follow the scratch work first, and then we'll write it up. Okay? Yes, Sarah.
Well, so how do you get that delta equals epsilon over 3 because it says that it's like greater than x minus 4? At the top.
So the game is this, right? The game is somebody gives you an epsilon and says, how close do we have to be to 4 to ensure this thing is within epsilon? This thing is smaller than epsilon. Okay? And so you look at this thing, and this is the same as that, right? And you see that it's this, right? It's this. So how small should this be to make this product less than epsilon? Well, if we make this thing smaller than epsilon over 3, then 3 times it will be smaller than epsilon, right? So that's what we'll do. We'll take our delta to be epsilon over 3. And then we see that whenever this thing is smaller than delta, whenever this thing is smaller than delta, namely epsilon over 3, then this thing is smaller than epsilon. Okay.
So it's only a coincidence that x minus c ends up down there in the 3 times x minus 4?
We're lucky, but it always happens in terms of if you have a line.
Oh, okay.
It always happens if you have a line. So yeah, we are. That's very smart, Gwyneth. We're lucky. Yeah, good. I should probably give you a bonus point for that on the exam.
Thanks.
Yeah. Okay. Yeah. Good. So okay. So here's how you would write it up. You'd say, we want, given epsilon, we want delta, so that if this is smaller than delta, then this is smaller than epsilon. Okay, you'd say, well, take delta to be epsilon over 3. Then, if this is smaller than delta, namely epsilon over 3, we see that this thing is 3x minus 4, which is smaller than 3 epsilon over 3, namely epsilon. So that delta being epsilon over 3 works for us. Okay. Everyone all right? Everyone all right? Except for me. Am I right?
This might have been what I was saying, but so if it doesn't work out, it worked out kind of perfectly.
Yeah, it worked out kind of perfectly,
It's like,
exactly. Yeah.
If it doesn't work out, that means the limit doesn't exist, or
Well,
what if you can't get it so that it's x minus 4?
one sometimes has to work a lot
Just work
harder.
more.
One sometimes has to work a lot harder to get it. Yeah. We're in this class. We're just going to stick with lines.
Okay.
We're just going to stick with lines because the idea is important, but all the tricks of getting the idea to work are not. That's not the point.
Okay.
The idea is the point here. Okay. So we're basically going to stick with lines. If you can explain, you know, okay, so I think everybody is able to if a line, it's easy to figure out what the delta is. It's going to be epsilon over the slope, right? Epsilon over the absolute value of the slope. Okay. So I think what's important for you is to understand why that delta is the right one, right? To be able to explain that that what it does for you, right? What does it do for you? It's the distance, so that if x is within that distance of c, then f of x is within epsilon of L.
Should the 3, the absolute value of x minus 4, it's less than 3, or is that epsilon?
Less than 3 times epsilon over 3.
Oh, okay, okay.
3 epsilon over 3, which is epsilon. Okay. Any other questions? I think, yeah, Claire.
Is delta always epsilon over the slope?
For a line, yes. For a line, it's always going to be that way. But suppose you have a quadratic,
Okay.
right? Suppose you have a quadratic x squared. Then what happens? Well, it's a little bit trickier, and there are ways to do it, but it's a little bit trickier. But anyway, the main thing for you is understand the notion of limit. That is, the limit exists. What the limit existing means is that given any tolerance, you can find a place where that tolerance is satisfied. Right? No matter how small a tolerance is required, you can say there's a place where that's satisfied. If you can do that for every tolerance, then the limit exists. Okay, that's what the limit existing means. Yes, Asha.
Does this someone say it's covering everything up to today?
Not today. Not today. So the test will cover everything up until the homework you've turned in now, but not today's work. Not today's lecture, and the homework for this section will be due afterwards, due on Friday. Okay, so not the day of the exam. Okay, so if you'd like to stick around a little bit, I have some homework to hand back.